So it's our pleasure to have Arnab Kundu from the Saha Institute in Kolkata. He'll be telling us about the synthesis of deep round plateau, black holes, fuzzballs, and semi-classical analysis.
Thank you. Thanks a lot, especially to Nick and Joseph for inviting me to speak here. It's great to see some old friends and meet new ones. So I understand that I stand between you and your lunch. So don't be too concerned about that. And I'm also in a bit of a, there's the food is too bad and there is too little of it kind of situation, but I'll try to contradict myself towards the end of it. So this is a work, or at least I'll be trying to tell you about a part of some ongoing work that we have been trying to do with some very smart and efficient people who I think took these ideas much more seriously than I did initially at the list. These people are, for example, Shumon is my student, Chetan is my friend, is a faculty member there. And the work started actually with Chetan's undergraduate student, Pritam. And then later on, we had Umit also join us. So it's going to be about something to do with spectral form factor, which I'll introduce in a moment, and certain things that we see, which seem rather interesting and robust to us. And I should tell you that I'm not really a fuzzball expert. So what I will try to do is I'll try to take that as my advantage and do things which might raise questions. And those are genuine questions. I will not be able to answer or address all of them. But what I want to say is that we are fully aware of these potential loopholes and problems and questions. And maybe I will, if I have time, I will comment on some of them. But not all, of course. So this is going to be an outline, very rough, and let's see how that goes. But I'll start with some motivating and introductory remarks about this object, which is a spectral form factor, and essentially some physics in it, what is generic and what is special that we expect from such things. Then I'll try to talk about a model. This is really going to be a very, very toy model, which you will see in a moment. And it's a very, very simple one, possibly the simplest thing that one can do. And it's a bit surprising that it was not done before this. But nonetheless, this is where I will introduce the model and then talk about some results and some remarks about ongoing works. And then, of course, try to conclude, which will be mostly open-ended statements, because it's not a closed story by any stretch of imagination. So that's the point. So before I get to the original picture, or before I get to the main theme of the talk, what I thought I would do is just tell you about something or sort of where I am coming from. And that, I think this point has been highlighted many times in this conference already, that dynamical aspects are rather interesting and important, of course, for black holes as well as any quantum mechanical system. And this perhaps is a very unique time in a certain sense, where we can actually set up a tabletop quantum mechanical experiment and watch its dynamics for a very, very long time. It's just a technical advantage that we have right now. And one particular interesting aspect that becomes very intriguing across many disciplines in theoretical as well as experimental physics is the notion of quantum chaos. By the way, I'll also mention a following statement and not elaborate on it anymore. But if you are interested, I'll be very happy to have a discussion on this. That if you try to think about dynamical aspects, then Wilsonian effective field theory and quantum the questions in quantum field theory can be subtle. At least there are confusions that I do not know how to resolve by a concrete calculation and so on and so forth. But nonetheless, it's not important. But if we start from classical chaos, of course, we all understand that, because it can be described in terms of classical trajectories and their properties. That's very clean. But once we try to take that idea and go to quantum regime, it's not just a single idea. It's in fact a zoo of ideas that sort of open up, and each of them have their own life and features. And I just have very broad brush fields that sort of emerge. And I will only be trying to talk about one such aspect, as you will see. But nonetheless, there are, this slide is just to tell you that there is a lot of conceptual things floating around these sort of statements. And why am I talking about quantum chaos? So let me try to tell you about that. So, well, I mean, that's the question. And as I said, well, there are recent experimental strides which make it rather possible for a quantum mechanical system to set up in your lab and watch it for a very, very long time. And why should I do that, or where are the surprises? That's what I'm going to try to tell you about. But before that, it's also kind of becoming clear that these ideas are making theoretical connections across borders and sometimes violating borders in a good sense. So that's a great thing. But the reason I want to talk about it here is because, I mean, when we want to think about black holes, for example, immediately we think about thermodynamics and its thermodynamic properties. But if we take a step back and try to think about thermodynamics and thermodynamic properties of any quantum mechanical system, the question, the modern perspective on that, even in a standard garden variety quantum mechanical system, is how does the system thermalize? Meaning, how does pure density matrix become or look like mixed density matrix in a quantum mechanical system? How does that happen? So there are these questions. This is a question that people are worried about, people are concerned about, and then people make progress with extremely innovative ideas all across disciplines, and that's one way to try an approach. So, for example, if I want to understand thermodynamics of black holes, perhaps I can start asking, how does a system which is like a black hole or a black hole microstate give me a thermodynamic description or thermalize? Suppose I pose the question in that way. If I pose the question in that way, then one corner of understanding, or at least modern perspective, is that you have to think about quantum chaos. Because if there's a notion of quantum chaos in the quantum dynamics of that object, it can give you a thermodynamic description. So if I'm thinking about a microstate, let it be a geometry or let it be a configuration or what have you, if it can show me some notion, some precise notion of quantum chaos, then it's probably going to give me a thermodynamic description. That's why that's the more or less outlook. Now, dynamics is a rather complicated object. How does time evolution is a very technically very complicated well, technically can be very complicated thing to analyze. But nonetheless, what seems to be true, more or less, for a large N system, for a system with many degrees of freedom, is the following: that the dynamics gives rise to various time scales. So, for example, one time scale is very familiar to all of us. Well, maybe all of them are very familiar to all of us. But so if in this room, if I treat this room as a quantum mechanical object, I do a local perturbation here, that perturbation will dissipate. That's the dissipation time scale. It's usually given by the inverse temperature. That's simple. But of course, there are also other time scales. For example, if I do a local perturbation here, in terms of information, I'm doing something, I'm inserting some information locally here. When does that, or how does that information become available to the farthest corner of this room? So there is a time scale associated to that, and that is called a scrambling time scale. And typically, the scale has well, for a strongly coupled system and so on and so forth, the scale has a log of s. And you can see that if it's a many body system or system with many degrees of freedom, then there's a huge gap. And interesting things can happen. Interesting dynamical things can happen. For example, out of time ordered correlators and so on and so forth. That has been explored in our community much more recently. But even longer, if you wait even longer, there's a time scale called Heisenberg time scale, which is basically given by the inverse of the gap in your quantum spectrum. So if you have a gap, if you have a discrete quantum spectrum, you take the minimum gap and take the inverse of it. And the inverse of it gives you essentially that Heisenberg time scale, which is the longest time scale for this system, leaving aside Poincare recurrence and so on and so forth. So this is where spectral form factor starts becoming important. And I will comment on that. So this is really what I will focus on. I'll not talk about this part. Good. So how do we even try and or start and address this question? Well, there are two broad ways. There's a sort of, I mean, I'm saying Euclidean, but it's not really going to be that important. But there's a semi-classical approach where we know that there are several fine-grained entropic quantities that can be captured within holography or within some notion of quantum gravity, but at the cost of some UV details. So what is happening at the UV is not clear, but nonetheless, you can do some things here. And there is also a microstate based description, which is essentially like fuzzballs and so on, where one tries to really construct these geometries, which are fairly complicated and rich in structure. But the question remains, how does a random matrix theory or a quantum chaos emerge in such systems? That's not immediately clear, at least. So what I'll try to talk about, as I said, is, well, it's a toy model that has interesting answers and hints, at best, I would say. And you can take the viewpoint, which is correct, that it's neither going to be a black hole nor a fuzzball. That's a correct statement, but it's not an interesting statement. Instead, what I'll try to do is focus on the simplicity and generosity of the observations that one can make from this. But this is a correct statement. I'm not going to, we don't have a so-called UV complete description of it. I might say something if I have time, but nevertheless. So the philosophy of this talk is going to be less is more. And well, of course, then I don't address if less is more, how much more will be. That I will leave, well, for later perhaps. Good. So what is a spectral form factor? One can introduce this in various ways, but if you think about a thermal two-point function, it's a very, very simple object and familiar object to all of us. So that's a thermal two-point function. There's a thermal density matrix, and O is just some operator, some standard local operator, let's say. I'm suppressing all the space arguments and so on and so forth. Now, if you evaluate this, the right-hand side is, of course, a sum over energy eigenstates that I can just get by inserting a complete set of energy bases. That's also trivial. But what happens is that, well, I mean, this is a hard object to compute, because unless you know the full spectrum, I cannot really compute it. But what I can do is, for example, I can take this summation and I can approximate it by an integral, because usually the spectrum has gaps which are not very large. And if I replace this sum by an integral, you can show that your thermal two-point function at very late times will be exponentially decaying. In fact, if the time is very, very large, so this basically goes to 0. On the other hand, well, yes. Thank you. Yeah. So yeah, exactly. So this T is dimensionless, if you wish. Right. Good. So, but if you given a quantum mechanical object, if you actually evaluated this sum, what will happen is that this will not go to 0 at very late time. It will become small but non-zero, and there will be oscillations around it. So if you like, it's a version of an information paradox, in the sense that if I approximate the sum by an integral, I get an information paradox. I don't get what I should get. I get it 0 where it should not be exactly 0. So a simpler diagnostic motivated by essentially this is similar. In fact, what you can do is you just compute your partition function. So don't even think about a two-point function. Just compute a partition function. Take your inverse temperature, do an analytic continuation in it, send beta to beta plus I beta, compute the mod square, and normalize it by z of beta square appropriately, so that at t equal to 0, this is just 1. That's just a normalization. It's not really important. Makes things slightly nicer looking. But if you write this object on the right-hand side, you get some expression like this, which is very, very similar to this one, and they will have similar physics here. And this is an object which was familiar to the quantum chaos community for a long time, and was brought probably to limelight to our community by this now famous paper in 2016, which I'll probably refer to a little bit. Okay, good. So let me give you the punchline right at the beginning. So what it say? What is the point? The point is that if I have a smooth density of states, then meaning that I do an approximation of the sum that I showed you by an integral, then at very large times, I should just get that the spectral form factor decays to 0, and therefore it doesn't capture the discreteness of the spectra. So this is a problem. Now, what happens typically is a diagram like this one. So let me briefly try and explain various parts of it. So as you can see, the blue curve here has three distinct pieces. One is where it is dipping, one is where it is rising, and one where it is plateauing. Hence the name deep, ramp, and plateau. That's yes. Yes. So the unit of time here. Okay. I was going to say that it's in terms of the inverse temperature, but so yeah, you can think of it. So I'm hesitating because I have here beta is equal to 0, but you can take beta to be very small, and this is the unit of measured in units of temperature. Yeah. Right. Okay. The unit, it will not be so relevant, in fact. But yes. No. What I mean is that there are not many dimensionful quantities floating around, at least in the setup that I will have. So you'll pretty much have temperature and time, not much more. So in general setting, of course, it can depend on various couplings and so on and so forth. Okay.
You will make a connection with your initial description in terms of the scrambling time, higher mechanics later on.
Well, yes. So the scrambling time, roughly speaking, will fall here. But I will not really talk about this part. Okay. I will talk about that part. That 10 to the 4 is the scrambling time for all practical purposes. Yes, good. So roughly speaking, the intuition is the following, that given any quantum mechanical system, if I do some local perturbation, well, that perturbation should decay and go into more and more degrees of freedom. Hence this dip. Hence things are going down, whatever this spectral form factor is. But if you wait long enough, then of course, at some point, onwards, there will be no change in the system, and that's this plateau. Now, what happens in the middle is not something that is intuitive, and it's in fact highly non-trivial. So whenever you have a ramp, by a ramp, I mean essentially a line of slope, constant slope, and I should mention that yeah. Well, let me come back to it later. So line of constant slope. So this is believed to originate from statistical properties of the spectrum itself. In particular, if the quantum spectrum has level repulsion of several kinds, not just one. So this is roughly speaking the three parts, and this is a picture that I took from our old paper, where there is still some numerical glitch here, which I assure you that it's actually a better one right now, but unfortunately I don't have that picture here. But the point is, the understanding from this picture is that if you have a ramp, then sort of you would be tempted to conclude that there is some chaotic dynamics going on in the quantum mechanical system. That's the folklore, if you wish. If there was no ramp, so for example, if you do a harmonic oscillator, you can do this calculation analytically, and then there will be no ramp. All that one gets is that there's a dip, and then there's a large it just keeps oscillating. That's all. There is no ramp. There's a clean distinction, which I'll also show in a moment. Good.
So you can estimate the Lyapunov exponent from the ramp?
From the ramp, no. So okay. So maybe what you have, I should have said that the Lyapunov exponent, etc., that you probably have in mind in terms of the OTOC, is what is called the early time chaos. And what I'm going to talk about now is late time chaos. Generally, these are isolated events. So there are systems which can show early time chaos, but no late time chaos, and vice versa. So I'm not going to be able to, or I'm not going to be talking about extracting Lyapunov exponent at all. But that's, yes. Yes. No. So I will show you one. So for example, I'll talk about harmonic oscillator, and there I'll have a picture.
But harmonic oscillator has definite frequencies, but the box
yes.
of gases can be very random, right? So box of gases.
No. So if it's an integrable system, so the understanding is the following. So if I have an integrable system, then well, maybe I can draw on the board. Is that? Yeah, I can draw it on the board if you wish. Something like this. And in fact, there are more characterizations of what you should get if you have an integrable system. Oh, sorry. I thought I had one molecule in mind. Sorry. Yes. So okay. Let me give it. This is integrable, but once you start making it chaotic, what will happen is that this object. Fair enough. Yes, but that's why I said integrable, right? So I'll come to the specifications in a moment. But basically, what happens is if it's a chaotic, so this is integrable. But if it's a chaotic object, you get same thing here, and then this is the ramp, which is chaotic, and also Plato. Okay, but yeah. Yes.
When one starts so abstractly in this way, and one hopes to learn something maybe about black holes, one thing I always like to get clear before I start is, like, if I take a box of gas, it also is a chaotic system.
Yes.
At what stage would I know that I'm not just talking about?
Coming to that. Yes, there are more to this. I'm just showing at this point some very qualitative features. But if you look a bit more carefully into this picture, there are better diagnostics. So yes, good. So okay, this I already said, and there's a one-line sort of slogan, if you wish. So the origin of ramp, it comes from level repulsion in the energy spectrum. So whenever you have a ramp, you can conclude that there is energy level repulsion, but that doesn't necessarily say what kind of energy repulsion. So I'll make this a bit more precise. And the general folklore, which is still somewhat qualitative, is that if you have a energy level distribution which is Poisson, then there should be no ramp. But if you have a Wigner-Dyson kind of energy level distribution function, level spacing distribution, then that should give rise to ramp. Okay. So that's, if you wish, that's one way of characterizing it. Good. All right. No. Okay. Good. So well, I mean, I have also said this to some extent. So what we are going to do is try and do somewhat ad hoc calculation, including a semi-classical kind of treatment to a picture which is motivated by a fuzzball like geometry. That's really what it is. And so for example, well, I mean, if I take a fuzzball motivated geometry, for example, then what I can do is, at a very crude level, I can think of a black hole. I can start from a black hole, and before I hit the horizon, I just put a wall. I just put a boundary condition from which modes will do certain things. So there will be nothing that will fall inside the black hole, but it will be reflected back. Quite clearly, this is not literally a fuzzball, definitely not, but that's where the motivation is coming from, and that's the model I will take. Now, I will not justify where this cutoff surface is coming from, what the dynamics of this, or what have I done to the theory, to the UV description, to ensure that there is such a boundary condition. But if you ask me, I can make some comments, but they are comments at the time being. Good. And what I will do is I will take this geometry, treat this geometry completely classically. I will not touch it. Now I will sprinkle in some scalar field, which are probes in this geometry, and then I will quantize these scalars in a semi-classical description. As simple as that. It's really, really simple. It's sort of similar to this brick wall model, etc., among other things, and so on. Good. So this is the technical details. It's really embarrassingly simple. So you start, for convenience, I'm going to do this calculation in BTZ because there's a lot of analytic control, but you can do this calculation, the same calculation in higher dimensions as well, but it would be much less clean in terms of algebra or whatever, calculus, etc. Good. So there's this geometry which has 3 coordinates. This time, there's a horizon at r equal to RH, the radial direction and an angular direction. And what you study is basically a probe scalar field. You can take it to be massive or massless, but the important part is that this is free. So it's really simple. It's a free scalar field, scalar field living in radius 3 in BTZ. So to solve this equation, well, we make a standard ansatz. We make this this phi, each mode, each angle and frequency dependent mode depends on the radius. So that translates into a radial equation. It's some Sturm-Liouville equation, if you like, some differential equation with some potential V of r that is given here. So you solve for this equation and you impose some boundary condition, and that's all there is to it. So let me just tell you what the boundary conditions are. We can all solve this equation. In fact, the solution of these equations are just some special hypergeometric functions, which are very well known, and it's just a matter of 5 minutes to find this out. Great. And now I have to tell you the boundary conditions. Well, there are 2 boundary conditions. One is that the ADS, since I'm in ADS, I should have probably emphasized that. I do impose a boundary condition at the ADS asymptotics, which is usual normalizability, but asymptotic boundary condition is not really that important. You can relax it a little bit if you wish. But what I will insist on is basically a Dirichlet boundary condition at the cutoff surface. So for me, r equal to r0 is the cutoff surface, which is happening, which is occurring, which is located right before, or at least before the horizon. That's by design. Okay. And just a comment that this particular condition, the details of this particular boundary condition is not that important, in the sense that I can put a Dirichlet boundary condition to be exactly 0 or something 0, or even you can take some Neumann boundary condition, or maybe even some combination of them. I mean, we can't really prove it as a theorem, but from sampling the space of boundary conditions, you can do that. So you get a, yes. Yes. So I'm going to, yeah. Yes. Any boundary condition which is not going to be an ingoing boundary condition at the horizon, that's what I meant. Yes. Good. So you get a spectrum, and because now this is like a standard undergraduate quantum mechanics thing. You have boundary conditions, you have solutions, and then you determine the quantum spectrum, which you can determine. In fact, this J part is rather easy because it's the angular part, so it just has to be integer valued. This omega is a frequency which somehow, the equations are analytically known, but the solutions, at least to us, are not known analytically. So but you can numerically determine them. And so this omega is leveled by 2 quantum numbers. One is n and one is j, and both of them are integer valued. And you can determine the full spectrum numerically. Great. So this is, roughly speaking, the first pass of computing the spectral form factor. So recall that this was the definition. This was just a definition that we started with. And now we have to compute the object. There's a bit of a problem because these omegas are known numerically, so the sums have to be evaluated with certain reasonable cutoffs that we have to put in as numbers. And when you do that, what you get is, on a log-log plot, is literally just this. What do I mean by this? Well, I mean, one thing that 3 things are immediately visible. First of all, there's this dip, that's clear. There's a ramp, that's also perhaps clear. If not, you have to take my word for it. But generally speaking, in this kind of business, whenever you get a spectral form factor or calculate a spectral form factor, they tend to be very noisy because of those phase oscillations. But this is really a nice plot. That's you have to believe me. And then there's a ramp also, which is growing. If you want, you can clean it up by some averaging mechanism. The averaging is not important for us at all. All I want to say is that if you want to see these pieces rather nicely sharpened, then you can do an averaging to see how sharp the signal becomes. That's really all. And one other important thing, which is technical, but nonetheless important, is that this plot is made, this is a log plot that we are making.
Where's the, what I call the echo time scale, the time it takes to start from some high radius and then fall, echo off the cap and come back? What time scale is that on here? Is that in the plateau? Or?
No. It falls in and comes back. That should be in the plateau. Yes, okay. That should be in the plateau. But yeah, but these are. I mean, you might have extremal black holes in mind. This is not. But yes. So whatever I throw in, if I wait long enough, it will come back. That's the message of this. So you can't fool everybody all the time. That's the if you wish. I mean, to put it colloquially. That's unitarity. Yes, but here it is basically starting to happen at that point, and then it remains the same because I have received everything. Good. So, so first of all, I declare, I claim it's that it's obvious that there's a deep ramp plateau, and I further claim that this is comparable to an SYK result. So the SYK model, which has become very, very popular to a lot of us, you can do this calculation in an SYK model or a variant of it. In fact, this famous 9-author paper that did exactly this calculation, and there the deep ramp plateau structure that you get is very similar to what I just showed you. And one other thing that I want to say here is, which I already said, is that we did not need to do any averaging. Because, I mean, why is that important? Because sometimes it happens that you take a model and then you do this spectral form factor calculation, and then you do some averaging, and you find suddenly that there's a ramp structure that emerges because of this averaging. So because of this averaging, there's probably some thermal notion that gets introduced into the system. So that I didn't have to do here. And people in this audience have already done this to similar, to a more CFT kind of calculation, I would say. And whatever I showed you in the previous slide, I just want to make it or emphasize that this is a rather robust observation, because I'm going to be really relying on the observation. It's rather robust in the sense that you can change your parameters if you wish. This observation doesn't go away. So and since it's numerical, I mean, you know, this is something that I have to do. There's a further comment that I want to make is the following. So suppose now there's a natural question that since I have this position of the Dirichlet boundary condition or the cutoff surface at which I can actually change that. I can actually take that cutoff surface and start sliding it towards more and more towards the boundary. So if I do that, the claim is the following. So if I place the cutoff surface close enough to the horizon where there is a very large redshift, the effect of large redshift remains, I see this ramp appear. But if I take it very far away, where the redshift is diluted in some sense, another way of saying it is that the black hole is almost gone from the picture, then there is no ramp. And in fact, it's a smooth transition. It's almost a crossover that if you really want, you can determine at precise position it is happening. It's going to be a bit tricky because it's numerical nonetheless. It's something that is quite visibly clear. Okay. And one other comment is that there are not many systems where, you know, this the spectral form factor, the existence of ramp, can be nicely tuned to no ramp physics in general. I mean, so that way it's a nice model also. So in terms of picture, this is the following thing I was saying, that if I did all these calculations in an empty ADS, no black hole whatsoever, then the spectrum is analytically known. In fact, it's linear. And if you just plot the spectral form factor, it will look like this. And this is sort of similar to what a harmonic oscillator spectral form factor also looks like. It's clearly no ramp. That's the main point. And what we get, just to sort of, if you wish, test our numerics, we take our calculation and slide this R0 to a very far region, farther from the horizon, we get something like this, which is, well, in terms of the physics that I want to capture, they are very similar. Okay, so no ramp at all. Good. So now comes the question, where is this coming from? So I'll try to make some statements about it. It's not going to be a completely closed statement in some sense, but there are some intriguing observations that I want to just point out. So first of all, first point, this is going back to your question, is that whenever I have a, sorry, what happened? Okay. Yes, no, yeah, it's fine. Good. So whenever I have a spectral form factor with deep ramp and plateau, he said that you can get this deep ramp and plateau for many systems, of course. If the system is chaotic in some sense, it will give you that. But if you for example make a log-log plot and try to fit the ramp with a line of slope 1, exactly 1, then it is believed that the system is random matrix theory, because you can actually start from random matrix theory and derive this statement that if your underlying dynamics is random matrix within random matrix universality class, you will have exactly you will have ramp of exactly slope 1. And what I'm showing you here is basically what our results are, and this yellow line is a line of slope 1. So
this is independent whether you take GOE, or G.
Yes. With the following caveat that since I'm doing it a log-log plot, there are corrections, but those corrections will not be visible in a log-log plot. You could ask, why am I doing it in a log-log plot and not just standard axis? But it's a numerical thing, so it's going to be very hard. I mean, it's hard to see the signal. Good. So here, all I want to say here is that at least one has to say the following thing, that whatever we are getting here, if it is not exactly 1, it's trying to be 1, certainly fine-tuned to be 1, right? So it's trying to be a random matrix theory. Now, I remind you that all we are doing is studying a free scalar field theory in a BTZ geometry, and this happens when there's a large redshift factor. That's all I needed, nothing more so far. And if you look a little bit close, you will see that the spectrum has an interesting feature. What is that? So if I plot, for example, the frequency with respect to the angular momentum, you will see that this plot looks like this. It may not, well, I mean, first thing that I want to point out is that, first of all, this is not linear, not like a harmonic oscillator spectrum. In fact, you can do a very nice log fit to it, and I'll come back to it in a moment. So there's a quasi-degeneracy, if you wish, and it's this particular feature which is giving rise to this ramp. At least that's what we are observing. Good. On the other hand, if you plot the level spacing distribution, which is really the one of the most crucial things that you can probably plot in this case, or compute in this case, you'll find for us the level spacing distribution looks Poisson. But since we have the ramp of slope 1 in the deep ramp structure, you can actually plot, if you wish, a projected level spacing distribution where you take, let's say, n to be some constant, n to be 1, but try to see how the level spacing distribution looks like as a function of j, and then it looks like this. Now, all I want to say here is that you will see that here there is almost nothing, which is to say that there is a strong level repulsion. But it's also not Wigner-Dyson, quite clearly.
What have you done to get the second form?
So so there are two quantum numbers. One is n, one is j. You fix your n, and you plot. Then you compute your omega, your level spacing distribution as a function of j. That's all I have done. So what I'm trying to see is basically, if you wish, sorry. Yeah. So I showed you that there is this dependence, right? There is some quasi-degeneracy, if you wish, of omega as a function of j. So that's this picture is essentially another way of saying that. J is the angular momentum.
But shouldn't to plot these, we should first separate out the global symmetry? Like, the repulsion is supposed to happen sector by sector in a representation of the symmetry group.
Yes. Yes.
Isolate a particular j, let's say j equal to 0, and then look at the level statistics within.
Well, that will have nothing. That will look like Poisson. Okay. So all I'm saying is that if you do that, that will look like a Poisson thing. But confusing, not the confusing, but perhaps the interesting bit is that you still get this. This is full. I mean, there's no truncation of any kind. Okay.
No, but I was asking about the Wigner plot.
Yes.
No.
Oh, sorry. Yes.
Yeah, this lower plot.
Yes.
What is this plot?
So this is exactly as I said, that so what we are trying to do here is trying to see in the level spacing distribution when there is a non-triviality that is giving rise to this ramp. Okay. So if you take the full spectrum and compute level spacing distribution, it looks like a Poisson distribution. So you would conclude that there should be nothing interesting, but there is. So now, what else could we have done? We could have done what you are suggesting, is that you fix J and look at the spectrum, right? But that will also have Poisson.
Okay.
So here, if you wish, we are mixing the global symmetry sectors. So these sectors are not these are not super selection sectors in some sense. They are not characterized by their symmetries or their charges.
But we don't expect Wigner-Dyson statistics if you mix up the different symmetry sectors. You don't expect.
But yeah, so this is not Wigner-Dyson, but there is level repulsion. All I wanted to say is that the origin, this is the only way it could give rise to a ramp like this. Which is to say, let me rephrase it in another way, is that the fact that this scalar field has an angular momentum is very, very crucial, and that is essentially what is contributing to the non-trivial features in the spectral form factor. It's another way of saying it. Okay, maybe, yeah.
Should I throw the mic?
So could it be that you are saying that as I fix n and I keep changing j, the eigenvalue will be maybe a linear function of j, at least for some range, approximately. So then they become sort of spaced, just like you would get from level repulsion in a matrix model.
Yes.
But if the spacing is all that you needed.
Yes.
So as a function of j, it's just like the L into L plus 1 over 2 kind of thing, which comes the effective potential.
Essentially.
So that's what's giving the spacing, and then you mimic the level repulsion, which you would have gotten from matrix model,
right?
Vander model.
Right.
Perfect.
Right.
Very nice.
That is exactly. Yes.
Very nice.
In fact, it will be slightly better also. Good. Okay. Spectrum.
Yeah, spectrum omega
J. So
yes,
it looks like J equals 0 is non-degenerate. It's like only one state. There's no n dependence for J equals 0.
No, there is. This is only n equal to 1.
Ah, that's only n equal 1.
Yeah.
Okay.
Otherwise, it's a complicated mess. Yes. These are slices. Yes. Otherwise, I don't know how to read this. Yes. Good. So I can go faster. All I want to say here is I can just state it. You can do a similar calculation, in fact, much simpler calculation in a Rindler geometry. So suppose you did a Rindler 2 calculation, where I remind you there is no way to excite an angular momentum. What you get, the spectral form factor for this object looks like this, which is like a harmonic oscillator. And that is perfectly nice. I mean, there's no problem. But if I just take a Rindler 2 times S1, where along the S1 I can excite angular momenta, I get out this deep ramp plateau the moment I have this. So all I wanted to say is that as long as you have a Rindler structure, a Rindler near horizon geometry structure, basically non-extremal horizons, and a compact part where I can excite angular momentum, you'll have this. It's fairly generic. Now, well, these are just comments. Well, as I said, Rindler, this is something I already said. Rindler calculation already shows that that basically that is all I need. I need just a large redshift to reproduce this, and that is where this non-trivial geometry is very crucial. There are two elements which are crucial. One is the non-trivial redshift. The other one is the angular momenta. That's all. And all other features in the Rindler calculation are qualitatively all identical to the BTZ calculation that I showed you. There's in fact no difference whatsoever. So So it should hold across general dimensions, but as I said, doing this calculation in general dimension is a bit more tedious and challenging because, well, BTZ is nice analytic, at least in some corners, but the other ones are not, unfortunately. So, but if you really want, you can do this calculation, and there is no reason that it should not work. Absolutely no reason. Good. And so what I said is that, well, this is a extremely crude first step, if you wish, or a calculation that seems to be giving us something which is rather interesting. And it's sort of like a fuzzball type geometry, but there are many features of fuzzballs, real fuzzballs, that this calculation does not capture. And in fact, you know, to be honest, I would have said that this calculation should not have captured anything at all. But the fact that it produces this spectral form factor in a non-trivial way is, I find, at least quite intriguing, among other things. And not just qualitative features, some more fine-grained details are also a bit surprising, which is, in particular, the slope of the ramp in a log-log plot is really trying to be a random matrix theory, although I showed you that there is really no random matrix theory yet. So now I'm going to do something slightly more, which is the following. So a little bit of structure in the boundary condition. So I said initially that I will introduce a Dirichlet boundary condition. Well, I will impose a Dirichlet boundary condition at the stretched horizon or cutoff, whatever you want. So at r equal to r0. But you can dress up that boundary condition a little bit more now. You can say that, well, no, I don't like this. I'm going to introduce a Dirichlet boundary condition, but on the right-hand side, instead of a constant, I will have a function of this theta is the same as what I introduced as psi, the angular direction. You can do this. And in fact, you can take a generic profile of phi 0 of theta. I'm not really sure what that means, or how should one define a generic profile of theta. But what you can do is you can take a function, do a Fourier expansion, and then pick out the coefficients of the Fourier expansion from a distribution. Now, a generic profile you can think of as, let's say, when the Fourier distributions have, when the distribution of the Fourier coefficients are picked out from a Gaussian distribution. Simple, right? In one limit, when let me just finish the sentence. In one limit, well, there are many advantages of picking out a Gaussian distribution, because in one limit you can make the Gaussian sharply picked and just pick out delta function, so that will just be a constant. And in another limit, you can make it a uniform distribution. That would be as spread out as you want, and so on and so forth. So as a function of the standard deviation of the distribution of the Gaussian that from where these Fourier modes are picked out, Fourier coefficients are picked out, you can mimic, you can interpolate across distributions. Yes.
I'm sorry. Yeah.
So the boundary condition is time independent?
Yes.
I see. Okay,
yes.
thank you.
Yes. That's important. Yes.
It's a wiggly wall.
Yeah. It's a wiggly. Yes. There is no. Yeah. There is no, in that sense, time dependency. Good. Great. So then I emphasize the following thing is that, well, you pick it out from a distribution, but once a choice is made, we are not going to do any averaging. I keep emphasizing this because averaging can introduce interesting thermal-like features just because of the process of averaging. So we are not going to do any averaging at all. Good. Now, good. So now I present you the following thing. Well, so as I said, I'll pick out a Gaussian distribution, and I will keep varying my standard deviation. So the calculation that I described so far was basically just this, which was, the boundary condition was just a constant. It's basically just one mode, if you wish, or a delta function limit of the Gaussian. Now, if I keep increasing the standard deviation, it looks like this. Standard deviation of the distribution. Yes. Sorry, this is there's somehow a lag. There was a lag, yes. Good. And now, if you keep increasing it further so that this becomes more like a uniform distribution, you get a distribution like this. Now, the blue curve that I have here is basically a Wigner-Dyson fit to whatever numerical plot we get. Now you can conclude whether this is Wigner-Dyson or not, but this is fairly close, I would say. This red curve is a points of fit to the numerical data that we get. This is also a very nice fit, I would say. So at least for that, I mean, the following thing can definitely be said, that as a function of the standard deviation, the level spacing distribution sort of interpolates from this kind of peak to Wigner-Dyson type peak to a points of peak. And if you keep track of your spectral form factor, you see deep ramp plateau here, here, and that goes over here, as I guess expected. Yes.
Can you go back to your boundary condition?
Yes.
So phi of r is phi naught of.
Sorry, I should have said phi of r comma theta on the left.
How different is that from having some sort of random potential?
No, not, yeah.
I mean, just introducing some kind of, random object sitting,
Yes.
that the things are bouncing off of. So
Yes.
this breaks. Theta is what again? It's the
angle direction.
Yeah. So yeah.
I think. Yes, that's what we wanted to do. That's what we wanted.
It's going to introduce some kind of random phase shift, basically.
Yes. Depends on the distribution.
So
Depends on the distribution. Yes.
right, but I'm just wondering whether I should be surprised that you got this Wigner-Dyson distribution.
My answer is no. Yeah,
it's just like introducing some kind of random phase in the propagation.
I agree. I agree.
In the phase shift coming
I absolutely
down
agree.
the throat and back up. Yeah.
So the reason I'm just to sort of comment on that, the reason I'm showing this is because previously I got a nice ramp, which was almost like or at least seemed to be trying to be a random matrix theory, but I did not have a Wigner-Dyson kind of thing. So all I'm saying is that if you take that structure, now put in some randomness, as you said, and then if I tune the standard deviation in the right regime, then you get a Wigner-Dyson distribution. But that fact is not surprising because there is a random boundary condition. That I agree with. Yes.
So
10 minutes. Oh, okay. All right. More than enough.
So
yes.
Sure. So you're studying the spectral properties of some Laplacian in some curved space with this brick wall boundary condition
Yes.
at the horizon.
Yes.
Why should this be related to the many body chaos that is discussed on the boundary? And because this problem seems unrelated to that. So what's the interest?
So all I'm computing is the partition function, if you wish, of the scalar part, right? And that partition function must be in the boundary theory, a partition function of whatever degree of freedom that you have inserted. That's just ADS-CFT.
But the partition function, if you compute, for example, 2-point functions of scalars, you put infalling boundary conditions at the horizon, not the brick wall.
Well, yes. So that's the point, right? I mean, if you put infalling boundary condition at the horizon, you'll never see a ramp because then your spectral form factor will always decay because infalling boundary condition will ensure that you have quasi-normal modes and not normal modes. So the fact that we get a that we get a ramp, that we get a plateau, is by design true. Because if I insist that I don't input infalling boundary condition, I get normal modes. With normal modes, you never get decaying spectral form factor.
The point is, what is the physics on the boundary that we are trying to compute with this bulk setup? Well, because you're doing some procedure in the bulk, but it's not clear what, because this is not a boundary spectral form factor for sure.
No, it is, right? I mean, so for example, if I take ADS-CFT, you take your geometry, you insert, how do you compute a 2-point function in ADS-CFT? You study a scalar field theory, which is probe, right? And in that probe sector, you compute your 2-point function. That's a boundary 2-point function, as long as it is expressed in terms of the boundary variables.
Yes.
Right? That's the same thing here. All I'm saying is that I'm studying a partition function in the scalar sector, in the probe scalar sector, which is a function of time.
No,
Time
but
is
you
the boundary
change the
coordinate.
boundary conditions in the deep IR, so you're not computing in standard ADS-CFT.
Yes, good, good. So what you are asking is, what does it mean in ADS-CFT to replace the ingoing boundary condition by a Dirichlet boundary condition? Is that a fair restatement?
Yeah.
Okay.
Yeah.
So this is an important question. I can only make a comment. It's not a precise thing. But the comment is the following. So if you think about this TT bar kind of deformation, then it is natural to think of TT bar deformation as a Dirichlet boundary condition, Dirichlet surface for that matter, somewhere inside the bulk. Now, normally what is done is that what you do is you input your Dirichlet boundary condition and keep the interior. But you could also do the following thing. You could keep your ADS conformal boundary and up to the Dirichlet boundary condition that you have introduced by deforming the boundary CFT. It could be along those lines, but I do not have a precise answer. Sorry. Yes.
Can I understand what you're saying in planar terms as follows? That if you did the calculation of the spectral form factor, 2-point function, whatever, with the standard black hole and black hole infalling boundary conditions, we'd get a permanent decay.
Yes.
That presumably is in contradiction with what you'd find in the true field theory in the boundary, because
Absolutely.
we're expecting a dip ramp plateau, and in some cases like SYK, maybe we can calculate it.
Right.
We're expecting that.
Right.
In that case.
Right.
And are you saying that if you replace infalling boundary conditions, presumably with a fuzzball, but if we can't do that with a brick wall, you will get a dip ramp plateau?
Yes, that seems to be the case. Well, all I needed, so there are few things. One is that, first of all, I needed not to impose the ingoing boundary condition, which is, you might say, is fuzzball motivated, because things go and then they hit something and then they come back. There might be a phase lag, etc., but that's a separate story. That's one. The other thing I really need is a large redshift.
A large what?
Redshift. So you have to have this thing happening close to the horizon, where GTT becomes very small.
Can I ask a question about that?
Yes.
So, okay. Fine.
Okay, so I'm almost done. So this is the picture. Great. So last comment. I said something about the logarithmic nature of a spectrum, and now you might wonder, this is just a child's play, but well, that's what we are doing anyways. So suppose I have some quantum mechanical system with a logarithmic spectrum. What is its spectral form factor? You can easily convince yourself that if you compute, sorry, if you just write down the spectral form factor of such a system, it will be a mod of Riemann zeta square. And there are mathematics literature which one of them goes by the name of Lindelof hypothesis. I'm not completely sure whether it's a theorem or a hypothesis, but let me just state the hypothesis. It says that the growth of Riemann zeta function has a certain feature, and if you take mod square of this, take a log of this, you will see that in a log-log plot it has slope 1. So in some sense, if I have a logarithmic spectrum, you might wonder, first of all, well, I mean, why is it seem to be giving me a ramp of slope 1? Well, this is not really an equality, it's an upper bound, but nonetheless, it's consistent with that statement, that property of Riemann zeta function, which I just wanted to mention, I guess, for fun. It's not a proof of anything, but it's certainly consistent with everything that we know, at least not violating anything anywhere, and it's a rather interesting observation. So let me try to conclude. Maybe there's a lag. Sorry. Yes, there is a lag. Yes, good. So it's essentially whatever I said so far. So there are non-trivial structures in the spectral form factor that exist without any averaging, without the need of any averaging, and so on. Well, I mean, one comment is that you can do all of this, of course, especially in lower dimensional models by invoking wormholes and replica wormholes. And there, generally speaking, at least to my understanding, is that getting a ramp is nice, but getting a fluctuation is a bit difficult. But because we are doing a semi-classical calculation, fluctuations are just there with the ride. There's nothing you have to do. So that's kind of a nice feature. It does raise a question, a slightly curious question to me at the very least, that, which is a bit broader, that when can I have, for example, ramp with features that would expect from random matrix theory, but perhaps not really a random matrix theory yet. When, I mean, random matrix theory implies one thing, but whenever I see that, it doesn't necessarily imply random matrix theory. So is there a necessary condition? In fact, there are some conditions that you can actually write down phenomenologically, which seem to be true. But to this audience, perhaps is a question that I will more or less end with, is can we make this a more honest and fuzzball geometry, which, with that, I guess, with the picture, well, this is the picture that that is taken from the 2016 paper, which is a SYK model, and this is our picture, and it's actually a slightly better one. Especially if this kink kind of disturbs you, I can assure you that's not a problem. But that's just a comparison. With that, thank you for your attention.
Okay. Okay, very interesting talk. Thank you. My question is following up a bit on Raghu and Vijay and also Samir's question. So firstly, just understand exactly what you're saying about holography, for instance.
Mm-hmm.
Can I rephrase your main message in terms of the inverse problem? So if I have a field theory in which I have a computation or expectation that I have this Dip-Rab plateau,
yes,
and I want to ask the question, what do I have to do in the bulk?
Mm-hmm.
Preferably by solving some equations, but initially as a toy model, what do I have to do in the bulk
yes,
to reproduce the structure by replacing the horizon with something?
Right.
And I think what you're saying is as long as you replace it with something which is close enough to what would have been the horizon such that you have a large redshift,
yes,
then even with some relatively crude reflective physics or possibly some randomness, you can actually reproduce this
yes,
Dip-Rab plateau. So the Dip-Rab plateau from the field theory doesn't tell us too much about the details of that structure at the horizon per se.
Correct.
Thank you. And secondly, can you quantify a little more precisely, maybe in terms of the redshift, this difference in behavior you had when the stretch horizon was far from the horizon, you didn't have this Dip-Rab plateau. When it was very close to the horizon, you did. Can you be a bit more quantitative on the kind of redshift or
well, yes, the answer is yes. I'm not sure if that will help you either, because well, it's some number that you know, between the as a ratio, it's going to be just some number that I'm not really sure whether that will help.
Well, I'm just curious. Yeah.
But one thing that might be a bit more, I guess, substantial is that you can ask whether I have to really place this cutoff or whatever, this abrupt thing at Planck scale away from the horizon or something else. The answer to that is also a bit, I mean, this calculation will not be able to tell me any of that. It will tell me that I can place this structure at Planck scale, but I can also place this structure at, let's say, a string scale, which doesn't have to be, you know, at the same level.
Yeah.
But as long, so all this is saying is that as long as something new is happening, if I place this cutoff at that point, then I get this.
Sure,
and if that cutoff is, I mean,
I guess I was curious as to your precision. Could it be several orders of magnitude larger than
oh,
the
no,
Planck scale, and you would still get this behavior?
No, that's not
okay, so it really has to be some kind of arbitrarily high redshift
yes,
to get this.
That's right.
Thanks.
Yeah. What I meant is. No. So here the choice is. So what I mean is the following. So I can think of the scalar sector as arising from fluctuations of the gravitational action itself, and because the gravitational action comes with the G Newton, 1 over G Newton, that's what I had in mind. So that's the.
You did some numerics.
Yes, of course.
So you chose some particular place to put your Dirichlet value.
Absolutely.
How did you choose it?
Well, that's just some number. So for example, you can choose. Suppose you choose some number close to 1. Let's say 1.01, for example. So you have to scan over. Well, this is a number divided by the horizon. So yes.
So what value did you use for your
What value of the
value did you specifically use
for you mean the ratio of yes.
As your cutoff scale.
Yes. So in terms of that, it's order 1, roughly speaking. So when I say it's close to 1, it's close to 1 in that sense. So if you take it to be, let's say, the cutoff surface, when the cutoff, so suppose this is the cutoff surface, suppose this is the horizon. So all I'm controlling is the ratio of the two. Okay, so the statement is when the cutoff surface is close to the horizon, meaning the ratio is close to 1. So I can take it to be 1.01, for example. This is like, oh, that I don't remember. But what I can say is that if I choose it to be, let's say 1.1 or 1.01, then you see this thing. But if you choose this to be 3 orders magnitude higher, for example, then that goes away.
Hey, also, I have one more comment. In these two plots that you showed on your last slide, I really think it's comparing apples and oranges, because it's not just the shape, like this dip, ramp, plateau thing that matters.
Sorry,
no, just on
one?
your very before the thank you slide, you had this.
Oh, okay, this one. Oh, that was just,
Yeah.
yeah, okay.
I mean, there's a y-axis. So on the top plot, the top value is, if you normalize it in a certain way, is e to the n square.
Yes.
It's supposed to be e to the 2 times the entropy of the boundary CFT.
Yes.
Whereas you're computing the spectrum of a Laplacian of a single scalar field, there is not going to be any n squares in the second plot.
No, of course not. So what you are asking is, what you're asking is this height, right?
Yeah.
Yeah. So that's going to be the entropy of this additional, the scalar degrees of freedom. So that's all we are really computing, right? So the partition function is of that scalar part. So the entropy is also going to be of that part. So
yeah,
but that may not scale with. Yes.
Yeah,
Yes.
but what I'm saying is that then the question about the fuzzball is really different, right? Like, because if the motivating question is how can you reproduce the first plot using fuzzballs, the second one is not really helping us because there is no n square in the game in the second plot.
Well, yes, hold your horse for a moment. So all I said is that in all these calculations are done in the probe limit. So what you can already ask is what happens when that scalar field back reacts. So the geometry will change. And now what I should really do is do a full geometric calculation, which I have not described. So all I'm saying is that this is perhaps a nice hint that something like that might happen. What you are saying is absolutely true. But it's also not within the scope of a probe calculation, for sure. By design, that's not there.
But we know that the empty, the double cone geometry, which is just an empty wormhole, does give you the right answer. And whatever this probe scalar you add on will be like a one loop effect on top of the stuff that has already been computed. So I just don't see how this will connect to some fuzzball or some redoing the calculation that has already been done.
Let me put it in the following way. Suppose I have suppose in this room I study some probe sector, some probe particles, and in that probe particles, they are really probe. They're just some small particles going around. In that sector, I find a random matrix theory kind of signature, a quantum chaotic feature, right? Then what is at least one natural expectation? If I start filling up this room with more and more such probe particles, then this whole room will eventually be a random matrix theory type, because those particles will now back react on this full object, and because they had a chaotic feature in themselves, it's rather generic to imagine that this will introduce chaos rather than make it less chaotic. That's the thing. But it is a probe calculation. You are right. Thank you. Oh. Of